Hey everybody, this is 11G, magnitude of friction paragraph. So it says a coin is set on a large turntable, a distance 4 meters from the center of the turntable. The turntable is slowing down so that the speed of the coin is given by the equation v equals 6 minus 2t. So let's write that out. It looks kind of like this equation here. V equals v0 plus a times t. So, whoops, sorry, that's not on there. So if that is our equation right here, then we can see that our initial velocity is 6 meters per second and that our acceleration here is negative 2 meters per second squared. So those two bits of information are given to us here. So let's look at the next pictures that they have for us here. It says the coin is in the location shown in the diagrams at t equals 1 second and t equals 2 seconds in each diagram. Draw the following 3 vectors. Make the vector lengths such that each square in the diagram represents either 1 meter per second or 1 meter per second squared. So first off, we're going to need a vector labeled v, representing the velocity of the coin at this instant. I'm going to do that for both of these actually, and then go back and do each of these for both times there. So to get the velocity, well, let's plug it into this equation right here. So at 1 second, we can plug that into this equation. So the velocity will equal 6 minus 2 times the time is 1. So it'll be just 6 minus 2. So the velocity is 4 meters per second. So let's add that to our, if I can pick up this piece of paper, time right here. So remember, it's going counterclockwise or clockwise here. So at this time, it would be going this way. So 1, 2, 3, 4. That will be the tangential velocity at 1 second. Let's go and solve that now for at 2 seconds is our other time. So that final velocity will equal 6 minus 2. In this case, our time will also be 2. So 2 times 2 is 4. So 6 minus 4 is 2. So it will be going 2 meters per second at 2 seconds. So again, we're going clockwise. So at this moment now, we'll only draw this out 2 squares. And again, that is the tangential velocity at that moment. Now, let's actually skip 2 because it actually, let's do the tangential acceleration. That's like the linear acceleration. And we can see in this equation, as we've already stated, that since this is basically the first equation here, negative 2 is the acceleration. And so negative 2 means in the opposite way that it's traveling. So in this picture right here, I'll label this a sub t. So the tangential acceleration would point opposite to the way that it's traveling. And it should be 2 squares long to represent 2 meters per second squared, negative 2 meters per second squared in the opposite direction. And that's just a constant value there. Finally, we need to label the centripetal acceleration. And so to do that, we're going to need this equation right here. Centripetal acceleration is equal to v squared over r. So in the first case here, we were going 4 meters per second. So 4 meters per second squared. Our radius is also 4. So we get 4 squared over 4, and that is a value of 4 meters per second squared due to the centripetal acceleration. So in this diagram right here, the centripetal acceleration points towards the center. So 1, 2, 3, 4, basically all the way touching the center there, and we'll label that a sub c for centripetal. And then in the second we have slowed down. So when we go to calculate our centripetal acceleration, it will still be v squared over r, but our v now is 2. So 2 squared over our radius of 4, that gives you 4 over 4, and that simplifies down to 1 meter per second squared due to the centripetal acceleration. So right here, we'll just have 1 block drawn in, and that is our centripetal acceleration. So last part here, for part B, it says the experiment is repeated with the coin set again at 4 meters from the center. This time 2 trials are performed where the turntable starts at rest. On trial 1, the turntable increases its motion very gradually, and the coin slips on the turntable surface when the coin is moving any faster than 6 meters per second. On trial 2, the turntable increases its motion so that the coin speed increases at a rate of 8 meters per second squared. That's a pretty decent acceleration, right? That's a good portion of g there. So, and the coin slips when its speed reaches 4 meters per second. In a clear, coherent paragraph length response that may include equation figures and calculations, but these are not necessary, explain why the speed to make the coin slip in trial 2 was less than in trial 1. So I'm not going to write the full paragraph out here. I'll just make the bullet points here. So let's just say this. When you are gradually speeding up, then we really don't have to worry about the linear acceleration. We only have centripetal acceleration to worry about. So, and that's supplied by the force of friction. So the force of friction just has to worry about making it go in a circle. The acceleration to get it up to speed is so small that it doesn't really have to worry about that too much. So, but when we go speed up quickly, so when we speed up quickly, or when we have a large acceleration as 8 meters per second squared is, then the force of friction not only has to be the centripetal acceleration, sorry, this sentence is a little bit of nonsense, right? The force of friction, I mean to say by saying equal causes, right? These force can't be equal to an acceleration. I can write this though, the force of friction is equal to the mass times v squared over r. That would be true. But down here, the force of friction has got to cause, let's draw it like that, a centripetal acceleration, and it's got to cause a tangential acceleration to speed it up too. So it's got to do two jobs at once, make it go in a circle and make it speed up. That's why this case is harder, and that's why it slips earlier.